or we can also name it as a change of scale property. And the statement is if Laplace of the function f of t is f bar s, then Laplace of f of at is 1 upon a f bar s upon a. This is the Laplace of a scale property. And we can prove this theorem also. This is a small article. We must know the proof of this article. By definition, I am going to prove it. By definition, the Laplace of f of et is 0 to infinity e raised to power minus st into function. What is the function? F of at dt. Now, by using a simple integration formula, we can use put et is some another function u, then taking the derivative a dt is equal to du. This we usually use in 10 plus 2 plus. Just see, lower limit is 0, upper limit is infinity. What are these limits? These are the limits of t. So if we put t as 0, you will get u as 0. So the limit of u is 0. And if you put t as infinity in this, you will get u is equal to infinity. So the limits are same now. E raised to power minus s. What will be t? From this equation, t comes out to be u. T comes out to be u upon a. And what is the f of at? At, the value of at is u. And what is the dt? Dt from this second equation can be written as du upon a. So this a is a constant. We can take it out. This is a 1 by a, 0 to infinity, e raised to power minus s by a into u. This is a, and this is f of u into du. You know that the Laplace of f of t, this is the definition we have written here, and the standard definition I am again writing 0 to infinity e raised to power minus st f of t dt. This is the standard definition. In 10 plus 2, we have studied that change of variable in a definite integral does not make any difference. What does it mean? It means if in place of t we take u, then the value will also be in terms of s, and that value will also be same as we get with the help of t. So it means by changing t to u doesn't make any difference to the value of this integral. Ultimate answer will be same, and that answer will be in terms of parameter s. So what is this? This is a function of parameter s. What is s? S is the coefficient of t here with the negative sign. So if we compare this one, if we compare this term with this, you just see this one, this integral. You compare this integral with this, what is the difference? In place of a dt, we have a du, and in place of ft, we have fu. In place of t here, we have u, but in place of s, we have s over a. Negative sign is same. It means if for this integral, this one, I am going to making a circle over there. If in place of this integral the value is m bar s, then in place of this integral, this one, on the same pattern, this integral, the value should be equal to 1 by a f bar s by a, by using the same logic, because the coefficient of u is s by a, and here the coefficient of t is s. If coefficient of t is s, we write m bar s, and if coefficient of u is s by a, we write m bar s by a. Now this is the same value we need to get here by change of scale property. So this is the proof of change of scale property, which we can use in the forthcoming questions. Next we have inverse Laplace transform. Inverse Laplace transform. And as we have seen, the Laplace of a function of t is f bar s. This was your standard definition of Laplace of f of t. This is f is equal to a function of parameter s. Then, if we take L to the right hand side, this L can be taken to the right hand side and it will become L inverse. Then what will it become? F of t is equal to L inverse f bar s. So this is L inverse mean inverse Laplace transform. It means inverse Laplace transform of f bar s is ft and a Laplace of ft is f bar s. We can use the example Laplace of 1 we have already done, that is 1 by s. Then Laplace inverse of 1 by s, by taking L to the right hand side, it becomes L inverse. And what will you get? 1 from the same function. Another example, we have done Laplace of e raised to power at is 1 by s minus e. This is also a standard Laplace transformation. And from this, we can find out Laplace inverse of 1 by s minus a is equal to e raised to power e. So for all the standard function, we can find out the Laplace inverse transformation of the functions. Similarly, this function can also be used for change of scale, first shifting theorem. You see, Laplace of e raised to power t and sine 2t, we can find out with the help of first shifting theorem. For this, we need to find out the Laplace of sine 2t. And the Laplace of sine 2t is 2 upon s square plus 2 square. This is the Laplace. But exponential function is multiplied. And what is the coefficient of t? 1. It means in place of s, we can write on s minus e. So, what does it mean? In place of s, we shall write s minus a here. This is s minus 1 square plus 2 square. So this is the Laplace of this function, this one. Similarly, we can find out the inverse. Okay, one more question. If there is a negative sign, there will be a positive sign. Bar s plus e. So L can be taken to the right hand side and we can find out the L inverse of that function also. So similarly, in another way, we can find out some more L inverse or inverse Laplace transformation of a combination of functions. Let us find out the Laplace inverse of, let us find the Laplace inverse of this function. The statement is s plus 1 upon s square 6s plus 25. This is 25. You just see. We have to apply shifting theorem over here. Laplace inverse of small adjustments we need to make in the denominator s square plus 6s by making the perfect square. What is the half coefficient of s? The coefficient of s is 6 and its half is 3. And what is 3? 3 ka square 9. 9 can be written here plus 16. The terms have been adjusted. 16 plus 9 is 25. So L inverse, in the numerator we have s plus 1. This is plus, this is 1. Divide s plus 3 square plus 4 square. You just see. Uh, when there is a s in the numerator, we have the formula of cos, because Laplace of cos of at, if you remember, the formula is s upon s square plus a square. This was your formula. But in case of sine, we have a in numerator and s in case of cos. So in the numerator of our question, there is a function of s. It means the resultant answer will be in terms of cos. And one more thing, s plus 1 is there and s plus 3 is there. So for applying the shifting theorem, the coefficients should be same. What does it mean? There should be s plus 3 minus 2, sorry. There should be s plus 3 and minus 2, because 3 minus 2 will become 1. Denominator will be same, that is s plus 3 square plus 4 square. Now you just see, you can separate these two functions. Laplace inverse s plus 3 denominator s plus 3 square. We have made in the numerator as s plus 3, because in denominator also there is the same term. We have to use the formula, that is 4 square, and the second integral is, this is a minus 2. Minus can be taken out by using linear property. This is 2 upon s plus 3. Uh, so this 2 cannot be written. This 2, because we need 2 over here. So this is in the denominator we have s plus 3 square plus 4 square. So this is a, now we can apply the formula here. If you compare the denominator, this denominator term can be compared with this one. And what does it mean? If we multiply Laplace of e raised to power bt cos of et, then we can find out the formula, another formula, by using first shifting theorem. What is the coefficient of t here? B. So in place of s, we can write on s minus b, and that is s minus b square plus a square. So this is another formula by first shifting theorem. from this formula. From this formula, with the help of this formula, we can get this formula. And if we use minus b here in place of b, then what will you get? If you use minus b here, you will write down plus and you will write down plus. Why I am using? I am using because our question is with this. So this is this is negative b, because in our question there is a uh, positive sign in the numerator and denominator as well. So in place of b we have a 3, and in place of a we have 4. So by using this same formula, straight away we can write down e raised to power minus b. What is b? dt. And in place of a we have 4. This is equal to cos of 40. And similarly, we will make adjustments over here. Here is 3 and here is 4. We need 4 here. And if we write down 4 in the numerator, I'm going to write down 4 in the numerator. Then we need to make adjustment. I'm writing 4. Then there should be 1 by 2. Because one extra 2 I have taken in the numerator. Then it will become 1 by 2. This is 2. This is 2 now. Similarly, we need to use in the numerator we have a constant, not s. In case of s in the numerator, we use the formula of sine. But in case of constant in the numerator, we will use the formula of sine, and the formula is Laplace of sine 80 is a upon s square plus a square, and if we multiply it with exponential e raised to power dt sine 80, then the formula become a upon s minus b square plus a square. But in our case, in this value, this one, numerator is 4 and this is also 4 square. So in our case there is a, this is a square. So a is clear, this is 4. And what is the b? Here is a b, but what is here? What is the value here? Then if we compare this value with this, b is negative 3. Then by using this formula, you can take L to the right hand side, and L inverse of this term will be equal to this term. So straight away using the formula e raised to power minus 3t, then that is sine of 40. So this is the Laplace inverse of this question. So in the same way, we can do more questions of Laplace transformation. The questions of Laplace transformation with the partial fractions are also very important. Partial fraction we do in the class of 10 plus 2. This is also another important question. L inverse upon s cube minus s cube upon s4 minus. Sorry, this is not the question of partial fraction. I will do the question of partial fraction. It's this one, s upon s4 plus s square plus 1. We need to apply the partial fraction and find out the answer of this question. This is the question of universal Laplace transformation again. Now, we can find out the partial fraction after making adjustment of some terms. This term can be written as s upon s square plus s plus 1 and s square minus s plus 1. If you multiply these two terms, simply we can say that this is mathematical algebra, which we do in 9th or 10th class, that how to make an adjustment of terms. So this type of function we are getting now by applying the partial fraction, because there are two quadratic functions in the denominator and a polynomial in terms of s in the numerator, then that can be written as as plus b, this is b divided by s square plus s plus 1, and similarly and the second function is a cs plus d, and this is s square minus s plus 1. On multiplying, we shall get s is equivalent to s is equivalent to as plus b into s square minus s plus 1 plus c as cs plus d into s square plus s plus 1. Now you know how to apply the partial fraction, equating the coefficient of like powers of s, s cube. The coefficient of s cube on the left hand side is 0 and on the right hand side is s into s square. What will you get? S cube, and the coefficient is a, plus similarly you will get the coefficient cs into s square, that comes out to be c. Similarly, putting the coefficient of s square, left hand side is 0, right hand side is as into s, you will get minus a, and similarly bs square plus b, and from here this is plus c, this should be plus c. Similarly d into s square is d. This is the coefficient of this s square. Similarly, putting the coefficient of s, left hand side is 1, and on the right hand side we have e, and we have minus b, and similarly we have c, and we have d plus. This is another equation. Similarly, we can find out the coefficient of a constant term. Left hand side is 0, right hand side is b, and plus d. Now, after making a simple solution of these coefficients, you need to find out the values of the constants. And after simple manipulations, we will see that a come out to be 0, c come out to be 0, and b comes out to be minus 1 by 2, and d comes out to be 1 by 2. You need to solve these equations simply by adding or subtracting. So we need these four constants: a0, c0, d, b. This is b. This one. This is b. This is b. B is minus 1 by 2 and d is 1 by 2. Now we need to substitute the values over here in this expression. We will substitute the values, and after substituting the values, you will get, you have to substitute these values a0 and c0, and if A is 0, this will be 0, and that will be B upon S square plus S plus 1, and C will be 0. Uh, Sorry, put the value of B also. Put the value of B. The value of B is minus 1 by 2. It can be substituted over here, minus 1 by 2, and similarly D is 1 by 2, and the denominator S square minus S plus 1. This is 2. Now you need to make the adjustments of this function and find out the Laplace inverse transformation. Let's see. Because we simply do the L inverse of this function. So L inverse of this function, this one, means L inverse of this. So L inverse of this function means L inverse of this function. Similarly, L inverse of this function and L inverse of this function. So we need to find out the Laplace transformation. Laplace transformation of this function. Now you need to make the adjustment. First of all, constants can be taken out. L inverse of 1 over S square plus S plus 1, and similarly constant 1 by 2 can be taken outside of the expression, and 1 over S square minus S plus 1. You have to make adjustment, minus 1 by 2 L inverse of, just see, making the perfect square, and that is the coefficient of S is 1, and 1 half of 1 is 1 by 2, and 1 by 2 square we need to add S square plus S. 1 by 2 square is 1 by 4 plus 1 is there, and 1 by 4 has been subtracted. Similarly, in the numerator there is 1. Similarly, we can do in the next expression also. That will always be S square minus S plus 1 by 4 again, plus 1 minus 1 by 4. Because 1 by 4 has been added, and 1 by 4 need to be subtracted. 1 by 4 has been added, and 1 by 4 we need to subtract from this term. So you can make another simpler expression over here, because this is equivalent to this given expression. So I am going to write over here, this is minus 1 by 2. Now the perfect square has been made, and this is S plus 1 by 2 square. And what is this? 1 minus 1 by 4. 1 minus 1 by 4, that is 4 minus 1, 3 by 4. And the square of the term 3 by 4 is square root of 3 over 2 whole square. Now we can close the bracket over here. Similarly, this is plus 1 by 2. Similarly, we can write down from this expression also. L inverse this is 1 upon S minus 1 by 2 square plus square root 3 by 2. This is square root 3 by 2 square. So this is the adjustment we have made for finding out the Laplace inverse transformation. Now we can apply the shifting formula also. Let us see. Let us arrange some of the portion of this is finding out the remaining solution. We know that by first shifting the theorem, because there is a constant term in the numerator, and here is a constant term of root 3 by 2. Now you need to make adjustment. What does it mean? Here should be, wait a minute, make a space. There should be an inverse. There should, if there is a root 3 by 2, then there should also be root 3 by 2 in the numerator. Denominator will be same. This adjustment we have to made for finding out the solution with the help of formula of Laplace transformation, and similar adjustment can be made in the numerator of this expression also. Root 3 by 2 s minus 1 by 2 square plus root 3 by 2 square. Now, if we multiply in the numerator with the root 3 by 2, then we need to divide here. Divide here means here should be 2 upon root 3, and here also should be 2 upon root 3, because this extra term we have taken in the numerator, root 3 by 2. Now, in the constant we have, first of all, this 2 has been cancelled with this 2. This is a minus 1 by root 3, because there is a constant term here. So that will be the formula of sine, and e raised to power minus 1 by 2 t sine root 3 by 2 t plus 1 by root 3. Similarly, 2 can be cancelled, and that is equal to e raised to power 1 by 2. You just see here is a minus sign, there should be plus sign. This is t, and this is a sine root 3 by 2. So this is the resultant of a Laplace inverse of the given function. You can also make simple adjustments over here if you want to make. By making it more simpler, you can simplify with the help of standard formulas. First of all, just see what is common. We have a sine root 3 by 2 t is common, and divide by root 3, this one, and in the numerator we have e raised to power 1 by 2 t, and there is a minus sign, e raised to power minus 1 by 2 t after taking common. For what purpose we are doing so? For making adjustment of the terms. And we know that the formula for sine hyperbolic function, that is e power x, e power minus x. This one, there is e power minus x divided by 2. Now this formula is similar. Numerator is same. There is 2 in the denominator, but there is not 2 any. Not a 2. So you need to make 2 over here. You are dividing by 2, you need to multiply with 2 also. Now we can apply the formula. What is x? That is 1 by 2. So by the formula, that is 2 by root 3 sine root 3 by 2 t, and what is this? This is sine hyperbolic 1 by 2 t. Here is t and here is x. So this is the final resultant of our given question of Laplace inverse transformation. This one. So we leave our class here. Thank you very much.
Thank you, sir. Thank you, sir.